Hello everyone. Today we shall discuss about the simple pendulum. How the simple pendulum acts as a simple harmonic motion. So today we are discussing about the simple pendulum. See here the simple pendulum. The simple pendulum. Now, how the simple pendulum, the motion of simple pendulum is a simple harmonic motion. So here we are uh, drawing a simple pendulum so that we can illustrate this as a simple harmonic motion. This is a rigid support, and suppose this is the vertical point, vertical line, and suppose this is the length, this is the vertical support, this is the length of the bob. Suppose this is the bob, and the bob has the mass m, and this is length is L of the string. So here we will find that there are three important factors. Suppose one tension T is acting in this direction, right? Towards the rigid support. This tension T is towards the rigid support. This tension. And one will see the weight of this bob is always downwards. So it is m into g. This is mg. M into g. And suppose this is angle theta, and theta is very much less. This angle is suppose theta. So we are getting to say this angle theta, this angle will also be theta, because this line and this line are parallel, so this angle will be theta, right? So if it is mg, then it will be mg cos theta. This line will be mg cos theta, mg cos theta. And you see here there is another direction in this way, there is 90 degree to that, it will be mg sin theta, it will be mg sin theta. So these are the various forces acting on the bob, right? So you see here, this is the tension T, this is the length of the string, the massless string L, this is mg cos theta, this is mg, this is mg sin theta. Now we will deal with all these properties, right? Suppose now the simple pendulum we are taking, we have drawn this is free body diagram, free body diagram, free body diagram. This is a free body diagram of a pendulum. Now what happens in this case? Right? Consider a simple pendulum. Let us consider let us consider a simple pendulum, a simple pendulum. Consider a simple pendulum of a small bob of mass small m, of mass small m, tied to an inextensible massless, tied to an inextensible massless string of length capital L. This has been shown here. The other end of the string is fixed to a rigid support. The other end of the string is fixed to a rigid support, to a rigid support, to a rigid support, to a rigid support. The bob oscillates in a plane about the vertical line to the support. This is the vertical line. The bob is oscillating in this about the vertical line. Now let theta be the angle. Let this theta, this one theta, theta be the angle, theta be the angle, theta be the angle made by the string, made by the string, made by the string with the vertical, with the vertical. This is the vertical line, with the vertical. When the bob is at the mean position, when the bob is in mean position, the bob is in mean position, then theta at that time is equal to 0, right? So there are only two forces acting on the bob, tension T along the string, you see the tension T along the string, right, and the vertical force of gravity mg. There are two forces acting. This is tension T and the vertical forces mg. If we resolve this mg into two directions, one is along this direction, it will be mg cos theta, and along this direction it is mg sin theta, right? So what we get, that there are only two forces, there are only two forces acting on the bob, acting on the bob, acting on the bob. The tension T, the tension T along the string, this is T along the string, the tension T along the string, and the vertical force, and the vertical force and the vertical force due to gravity, So here you can see there are two forces, one is T and one is mg, and this mg can be resolved in two components, one is mg cos theta and another one is mg sin theta, right? So what we get, the force mg can be resolved, the force mg, this can be resolved into the component, can be resolved into the component, mg cos theta along the string, mg cos theta along the string, and mg sin theta and mg sin theta and mg sin theta perpendicular to it, perpendicular to it. So the motion of the bob is along a circle of length L. Since the motion of the bob, since the motion of the bob is along a circle, of length L, and center at the and center at the support point, and center at the support point, center at the support point, center at the support point, center at the support point. The bob has a radial acceleration. The bob has a radial acceleration, has a radial acceleration, radial acceleration. The bob has a radial acceleration omega square L, and also a tangential acceleration, and also a tangential acceleration, tangential acceleration. So what we get here, that the bob has a radial acceleration omega square L and also a tangential acceleration. The latter arises in the motion along the arc of the latter arises the latter arises the latter arises the latter arises since the motion latter arises since the motion along the arc, along the arc of the circle, along the arc of the circle is not uniform, So we are getting two acceleration. One is radial acceleration, another one is tangential acceleration. The radial acceleration is provided with the net radial force T minus mg cos theta. The radial acceleration is provided by the net radial force, that is radial force T minus mg cos theta, right? For the tangential acceleration, while the tangential acceleration is provided by mg sin theta. So here you see, again I am drawing the pictures of this one. This is the rigid support, and this is the vertical line, and this is the bob. So here you have two forces you are getting. One is along the T, along the string, and this the length of the string is L, and it has two forces acting. One is tension T and one is mg, that is weight of the bob. This mg can be, this is angle theta, therefore this angle will be also angle theta. So if we resolve this mg, it will be mg cos theta, and perpendicular to this it will be mg sin theta. So what we are getting two forces. One is this force, the radial force, and one is two acceleration. One is tangential acceleration, radial acceleration, and tangential. Here you see the radial acceleration is equal to radial acceleration is equal to T minus mg cos theta, and tangential acceleration, and tangential means this one, this is tangential, tangential acceleration tangential acceleration is equal to mg sin theta, equal to mg sin theta, right? It is more convenient to work with torque. It is more convenient, it is more convenient to work, it is more convenient to work with torque, with torque, with torque about the support, about the support, about the support. So the radial force, since the radial force, since the radial force, since the radial force gives zero torque, radial force gives zero torque. The radial force gives zero torque. Torque tau about torque, tau about the support, about the support is entirely provided, is entirely provided by the tangential, provided by the tangential, by the tangential component of force, by the tangential component of force, by the tangential component of force. Therefore, tau is equal to minus L into mg cos sin theta. So the torque along this is L, this is the length L into mg cos theta and negative. This is the restoring torque. This is the restoring, remember this one. This is the restoring torque. This is the restoring torque. This is the restoring torque. This is the restoring torque that tends to reduce, that tends to reduce, that tends to reduce, that tends to reduce angular displacement. Angular displacement tends to reduce the angular displacement. Reduce angular displacement. Hence the negative sign. Hence the negative sign. That's why it is negative sign. By Newton's law of rotational motion, we know that by Newton's law of rotation, this is equation 1. We know that equation 1. Now we go to the next thing, that is by Newton's law of rotational motion. By Newton's law, by Newton's law of rotational motion, the Newton's law of rotational motion, tau is equal to I into alpha. And also we got where I is the moment of inertia, where I is the moment of inertia, I is the moment of inertia, I is the moment of inertia of the system, moment of inertia of the system about the support, about the support, about the support, and alpha is the angular acceleration, and alpha is the angular, alpha is the angular acceleration. acceleration, and alpha is the angular acceleration. Thus, what we get, that tau is equal to minus L into mg sin theta, mg sin theta. This is equation 1. And another tau we are getting it as I into alpha, I into alpha. So by equation 1 and 2 we can write that I alpha is equal to minus mg sin theta into L. This is equation 3. Or you can write, or alpha can be written as alpha is equal to minus mgl by I into sin theta. Right? We simplify equation. You simplify this equation. We can simplify. We can simplify equation 4. We can simplify. We can simplify equation 4. Equation 4. If we assume that the displacement theta is small. We know that sin theta, we know that sin theta can be expressed as sin theta can be expressed as sin theta is equal to theta minus theta cube by factorial 3, theta cube by 3 factorial plus theta 5 by factorial 5 plus minus, getting this value, where theta is in radian, so we are getting this expression. Now if theta is very small, if theta is small, sin theta can be approximated by theta, and can be written as alpha is equal to minus mgl by I mgl by I. We are writing here so we can write this as that alpha is can be written as in this way, that alpha is equal to minus mgl minus mgl by I into theta. So this is equation 5. Right? Now here we will find that if we find the angle, so what we get, that alpha is equal to minus m into g into L by I into theta. This is equation 5. Right? Now we can find out a figure. We have made a table and we have listed the angle theta in degrees. We have listed we have listed the angle theta, listed the angle theta in degrees, its equivalent in radians, its equivalent in radians, and the value and the value of the function and the value of the function sin theta, value of the function sin theta. From this table, it can be seen that for theta as large as 20 degrees, sin theta is nearly the same. Sin theta is nearly the same, not same, nearly the same. Sin theta is nearly the same as theta expressed in radians, Now here is a table. You see theta in degrees and it is in radians. So theta, we have got a table, theta in degrees, and this is theta in radians. And here you find the value of sin theta. For 0 degree, so sin 0 degree, the radian will be 0 radian and the angle will be 0 here. For 5 degrees, the radian will be 0.087 and sin theta will be 0.087. For 10 degrees, the theta in radian will be 0.174 or sin theta 0.174. If it is 15 degrees, then it is 0.262 and sin theta will be 0.259. And if it is 20 degree, then theta will be 0.349 and sin theta will be 0.342. So what you can find here, that here what we find that alpha. So here what we find that up to, it can be seen that for theta as large as 20 degrees, sin theta is nearly the same as theta, right? Sin theta is nearly same as theta. You see, this is nearly same as theta, right? So what you can say, same as theta, that is in radian, same as theta, nearly same. 0.87 is 1.74, 0.262, nearly it is same, 0.259, it is 0.349, 0.342, nearly it is same. So the sin theta is nearly same here. So what we find that this equation 5 and this equation, that is, if we compare this with this equation, that is this one, 13 point, this one, A, acceleration as equal to minus omega square x, This is a simple harmonic motion, right? This is alpha, so these are same, right? So if we compare equation 5 and 6, equation 5, equation 5, equation 5 is mathematically identical to equation 6, right? Equation 6, except the variable is angular, except the variable is angular, except the variable is angular displacement. Variable is angular displacement. Hence we have proved that for a small cube, the motion of the bob, the motion of the bob is simple harmonic, right? So by comparing equation 5 and 6, comparing equation 5 and 6, we get what you get. You see here, this is omega square x. Omega square means this value, right? That it means we can write omega square is equal to m into g l by I. Therefore, it can be written as omega is equal to root over mgl, root over m to g into l by I, right? And time period is, you know that time period is 2 pi by omega. We know that this is time period is 2 pi by omega. So we get the time period here as t is equal to 2 pi by omega, means this value. Therefore root over I by mgl. This is the time period of a simple pendulum, right? Now since the string of the simple pendulum is massless, now so what we get, 2 pi root over I by mgl. We are getting the value here as, we are getting the value that t is equal to, capital T is equal to 2 pi root over I by mgl. This is equation 7. Now since the string of the pendulum, since the string of the string of the simple pendulum, the string of the simple pendulum is massless, the moment of inertia I is simply ml square. So if you write ml square, then you are getting t is equal to 2 pi root over ml square, I is ml square, by mgl. So at the end what we get, t is equal to 2 pi root over L by G, right? L by G. So equation 8. So we are getting equation 8. So equation 8 equation 8, the well-known formula. So the equation 8 is the well-known formula, for time period, of a simple pendulum, of a simple pendulum. So what we get here, that the time period can be written as t equal to 2 pi root over L by G. That means this time period is dependent only on the length of the pendulum, not on the mass of the bob. So time period, if you take a small mass or a big mass, it doesn't depend. The time period depends only on the length of the pendulum. So in this way you can define the simple pendulum, right? So in simple pendulum, time period is given by t equal to 2 pi root over L by G. This is the time period. Thank you everybody for watching this video.